is called the Metropolis Algorithm. What is the Metropolis Algorithm? It is an algorithm to simulate from a distribution, or simulate samples which would form a distribution. So let's just say the book has a very nice example. If you want to read it, I'm going to use a different one. Let's just same idea of it. Let's say I have choices for what should we go? Mexican food?
We did Mexican food,
Indian food? Okay, so what do we like?
curry.
What kind? Instead,
We found what we liked.
ramen,
Udon if you want.
udon,
Very simple. Don't put mac and cheese there.
Good gift.
Lasagna.
pasta.
Yeah.
And lastly,
Pasta.
what is that one? Rice.
Sure.
Rice noodles are fun though. Just saying. But okay.
All right. You could do.
Egg noodles.
Okay. I think that's
Okay.
pretty honest though.
I mean, that's good enough. As long as you get the idea. Of course, in practice, we can't use names, so we'll use numbers 1, 2, 3, 4, 5. No specific order. And we are going to have some size associated with it. So let's just say 2, 4, 8, 1, 3. So they don't have to be probabilities, even though they look like a discrete probability distribution. They don't have to be probabilities. They're just relative values relative to the previous state, what value we have, relative to ramen, what preference do we have toward from. Fine. So here's the thing. If I start with some arbitrary state, initial state, let's just say I start with ramen. And I had ramen and I would like to know where to go next. And which state should I go to? Well, there are a couple of possibilities. Oh, well, let's start with the third instead. Ramen would put us at 0. I don't want to get there. So third. If I start here, I have 2 options. Yes, either move to udon the next time, or go to ramen. Yes, but then there's also the possibility that I just stay where I'm at. Yes, get further next time also. And from once I decide where to go, let's say if I went over to udon, over here, I have a choice of either going to pho or going to pasta, or staying at udon, correct? So how do we decide? Well, if you are at udon, where are you more likely to go?
You stay at udon?
If something else is proposed, if I propose you either 2 or 4, which one would you go to? 2. Why? Because the relative is higher over here. If I propose ramen or egg noodles, you would go over here. Yes?
Yeah.
So that's what we call a target distribution. What I have here is a target distribution. The book uses the notation theta, so I'll just stick with that notation, even though in the context of Markov chains, It is always ij. You go from state I to state j to state k and so forth. But book uses theta. Don't confuse this theta with the parameter itself, even though they are related, because the target distribution is nothing but the posterior distribution that we are trying to sample. Good. So suppose I have theta c.
Target distribution is the posterior.
Yes. I think the book doesn't differentiate, just calls it as current state. And call it theta c. And the next state is just theta plus 1. That would be the proposed state. Theta p. Now, of course, the proposed state could be theta minus 1. Yes. So this is just an example. It could be theta minus 1. So how do we decide to move? So we want to move in a way defined by the target distribution. The probability that you move would be equal to the minimum of, not the probability. We're not talking about the probability, but we're simply talking about the density or the value over there. So P of proposed divided by P of the current state, comma 1.
Comma 1.
Yes.
Is a minimum.
Minimum of those two.
So, okay, all of those suck and one fills. in.
Yes. So if P of theta P is greater than P of theta C, what would the move probability be? 1. So if it is 1, then what are you trying to say? What does the
You will definitely.
definitely move? This is a definite move.
So the chance of leaving is greater than the chance of staying. Well,
The
the
chance,
chance of going to some proposed state is bigger. Or if they're all bigger than where you
Right.
currently are, then
Yes.
you'll definitely go somewhere.
yes. So if this is bigger, the proposed state value is bigger than the current state, this number is going to be over 1. The minimum of those two will be 1. So you will definitely move. Does that make sense?
The reason why it's a minimum, comma 1, is just so our probability doesn't.
Exactly, we want to move again.
Just don't go over 1.
Yeah,
Okay. Now,
So simple.
if that is not the case, then we would have some probability. So if that doesn't happen, otherwise we move probabilistically. So otherwise we move probabilistically. The book does use P and C, but explicitly calls it as proposed and current. So once we decide that that didn't happen, that leaves us with 1 or 2 options.
Move or not.
Depending on meeting of a certain threshold or something, like.
Right, so should we move or should we stay? Right, that'll be the question. So how do we come to that decision?
One-sided die.
Okay, so one way to do it is simply, use another probabilistic mechanism, right? Now, I may say, well, I'll make that decision based on, a six-sided die and put a threshold and then use that threshold to make that decision. So you have to come up with a probability, and in statistics, how do we generate a probability? A single probability is simply generating what type of random variable?
Or normal.
Normal. A probability. We want to generate a probability. We can use a normal, but the simplest one would be uniform, right? Uniform 0, 1. So to move probabilistically, we are going to simply generate a uniform 0, 1 value. I'll call it U. If the generated value is between 0 and the probability of moving, then you move. Otherwise, stay. Distribution, which is the target distribution. One, we should be able to generate this uniform, which we can. And we need to have a proper proposal distribution, something that will propose states properly. Now, we can propose things uniformly if we have to, but later on, when we do a continuous version, we need to use distributions such as normal, because we need continuous values. So this process is also called a random walk. Now, or a drunkard's walk. Think about, you start over here, yes, and if you feel like moving, if you think, oh, I can move, you take a step forward, and then you get to the step and you kind of feel, oh man, I'm just going to can't go. So there are only two possibilities. You either stay or something pushes you over to, back where you started, yes? So this entire process, the algorithm, is a simple random walk. It comes in time series also. Time series, it is not a stationary series. So it'll go all over the place. And it always depends on the initial state that you choose. So for instance, if you select an initial distribution, goes back to Markov chains, you have an initial distribution. Over the long run, you end up getting a steady state distribution. So it depends on where you start. So if you started here, you would get a path that will lead you to a steady state distribution. Compared to here, you'll have an entirely different path. So again, going back to the drunkard's walk, think about where you started it. You either started, on the curb, or you started, behind a car, right? They will lead different paths, yes? Because, for instance, curb, you could have fallen or, tilted. Something could have happened, right? So depending on which state you start, your trajectory of attaining the steady state distribution will change. However, at the end, you will converge. Does that make sense?
All steady states are the same regardless of.
Yes,
initial
and
movement.
the steady state distribution that you're going to converge to will be this. So that makes sense. And then intuitive sense, if I'm making decisions based on this, if I'm going back and forth
Yeah.
based on this, I'd better converge to this. Yes? It should make sense intuitively, because all my decisions are determined by this distribution. So sooner or later, my behavior will end up being this distribution in terms of transition. And that's when you hit steady state. That makes sense. Again, to attain steady state in the Markov chain, there are conditions. I won't get into all that, but we need to satisfy those conditions. One of those conditions is that having a recurrent state, and that will mess up getting a steady state distribution. Any questions?
So in the previous example, we had like 1 could go to 3. Are we talking about the same thing here as well? Could we go?
Good.
Yeah,
So here we cannot jump 2 steps.
okay.
We're just going to jump, 1 step forward, 1 step back. That's how we're going to define this.
So that means that this is different than a Markov chain?
In a sense,
Okay.
one case of a Markov chain,
Oh, okay, okay.
right? There are multiple cases. So
So
this
it's a
is one
linear,
case.
it's a linear chain.
Yeah, it's
Yeah.
a single case of a Markov chain. There are multiple chains. This is one of the cases is a random walk.
And all the states beyond plus or minus 1, which is a probability 0.
Yes,
Okay.
yes.
Okay, this is like a less technical question. I just want to be reassured. But like looking at this, if you can only move 1 step at a time, it looks like, let's say you make it to udon, you're almost never going to pasta. And even if you make it to pasta, you're less likely to even go to egg. So it feels like pasta is gatekeeping egg. But will that not matter in the eventual distribution?
No.
It'll end up there at some point, it'll still end up at egg at some point.
Yes. And I'll do that in a second. That's why
It just feels like they would affect each other.
it will work in the long run. So there is something called in Monte Carlo simulations, there's something called a burn-in period. So the burn-in period is the initial time where you'll be generating samples that are actually useless or before it's reaching that state. And if you use those observations or samples, then you'll mess up your whatever algorithm that you're doing. So the initial set of samples people throw away, the burn-in samples. So, so the idea is we are going to go back and forth, and converge to some distribution.
Is it linear, so you can never go from wrong to egg?
I can't, no, you cannot.
Not a loop.
That was loop.
You cannot. That's why I said this is one case of, several
Monte
Carlos. You're right. Now, why does this work? There are 2 explanations that the book gets over. I'll do both of them. One involves matrices, the other one doesn't. We'll start with the simple one. So, probability, you start at, say, theta. You move to theta plus 1. Yes? So that would mean a state is proposed and you accept what was proposed and you make a move. Correct? So there is a 30% chance that you would either accept or reject. Yes. And that acceptance is determined, after you accept, whether you move or not is determined by this. So that initial decision and this. So multiplication rule.
So there's there's two
Yes.
steps. There's the deciding to move and then the accepting the decision.
No, accepting the initial proposal.
So
Whatever that was proposed, should we even take it into consideration or not? 50% chance. Right?
so there's a 50% chance you ignore the proposal anyway.
Yes.
Because you might go forward or backwards.
Yes.
Or stay.
Or
Oh,
stay.
so there's two of them. It could either be +1 or -1.
Yes.
Okay.
So you can go either way. So it'll be 0.5 multiplied by the move probability that you have. That move probability in this case would be the minimum of, this is not a probability, this is actually some value. Once again, this goes back to the proportionality in posterior distributions. We don't care if it happens to be a proper probability density function or not, we really don't. So it doesn't matter as to what we have here, it always normalize and bring things back to shape. So probability of θ1 move divided by probability of θ. Yes, comma 1. Correct. You're proposing θ1. So θp, not θ1, θ plus 1. So θp, θ plus 1, θ current value is θ. Yes. The second case, mind you, can also go to θ from θ to θ minus 1, not doing it. 50-50 chance going this way or that way. So 0.5, that's where it's coming from. The second case, you start at θ plus 1 and you go back to θ. Yes, and that would be 0.5 minimum of probability of θ divided by probability of θ plus 1. Yes,
It's always a 50% chance.
Yeah.
this will always be 50%.
Even if you're on the end and you only have one option, do you still write it in that way?
Yes.
So like if you're at 1 and your only option is to go to 2, still leave it at 50.
Yes. Because it's going to get cancelled with it. Now, you're looking at the relative probability of moving. So moving from θ to θ plus 1 divided by θ plus 1 to θ. That would simply be 0.5 minimum of probability of θ plus 1 over probability of θ, comma 1.
What's the motivation again for dividing them?
Finding the relative probability of transition.
Can you interpret?
Give me 1 second. So θ over θ plus 1, comma 1. Now, the number of the proportion of you going from θ to θ plus 1 divided by the proportion of you going from θ plus 1 to θ. Eventually, it has to converge to what value if you are at θ? 1.
Be the same.
What should that relative value be? You know, you're going back and forth between θ and θ plus 1. So eventually, when you get to the state θ, where should you go next?
theta plus one.
Theta plus 1. So that's why we're trying to find the ratio going from theta to theta plus 1, back to theta plus 1 to theta.
This is like, so if it comes out to 0.4, it means you go up usually 0.4 at the time, down 0.6.
What do you mean?
Like if the, so if the probability up, let's say it's 0.4,
Okay.
and then the probability down was 0.6,
Mm-hmm.
then that would come up to 2/3.
Yes.
So how would you interpret the 2/3?
Well,
You move down 2/3 of the time,
yes.
so it's the ratio of moving down.
It's not necessarily the ratio of moving down. So if I'm in state theta, right? And my decision to move to theta plus 1 is defined like this. And from theta plus 1, I'm coming back to theta. Yes, the position is determined by this. Over time, the transitions of me going from theta to theta plus 1, theta plus 1 to theta, that proportion should end up with what value? Well, that's not. Maybe I'll write this.
Sure.
Okay, that was easy. Yes.
Could you explain the 0.5?
I mean, actually, honestly, question about the 0.5. Is it, should it always be the same?
What do you
Or
mean?
should the 0.5 on top
Yes,
always
it's
be the
always
same?
0.5.
Oh,
Yes,
is it always 0.5,
times.
no, 0.5 in general? Could it be a different number?
No, it's always.
Always 0.5.
Because it's like you have two options, left or right.
Okay.
So you have half left.
Let's say moving to theta plus 1 is bigger than moving to theta.
So then it would be-
Or if the value that we have for theta plus 1 is bigger than theta. So what would the numerator be?
Are those the same numbers? No,
1.
we're looking inside a little bit.
Yes.
Okay.
So that would become 1, correct? What about the denominator?
That would become,
If p of theta plus 1 is bigger than theta 1, it should be that value, yes.
So is the
What?
P of theta plus 1, it is not a probability.
Yes.
It could be any number at all.
Huh?
The P of theta plus
Could be any number.
is not.
I mean, this is like here,
Like
we're
here.
picking it up from here, it could be any.
Okay, so it could be like 8/1.
The probability of theta plus 1 over theta.
8/1.
if you're at pasta and you want to go to udon.
Oh, yeah, yes. Now, the second case, P of theta is less. P of theta is greater than P of theta plus 1. Right? If P of theta is bigger than P of theta plus 1, that's going to be smaller than 1.
So it's always the same.
The numerator would be
The
P of theta plus 1 over P of theta divided by 1. Yes? Now, the equal part is not going to matter here, right? If they are equal, it's minimum of 1, 1, right?
That's nothing.
Which,
There's one.
you move.
Yeah.
You definitely move.
Yeah.
Correct? So, because that's the move probability. So, if I rewrote that, the first case, P of theta plus 1 over P of theta. Same here, P of theta plus 1 over P of theta. what would the probability of staying be if moving from theta to theta plus 1 is that, and theta plus 1 to theta is that?
It depends on the failure, like the minimum part, right?
Well, we're keeping the minimum. I don't want to get rid of the minimum. I haven't made the decision yet.
But doesn't it depend what that decision will be?
I mean, that's just,
I'm going to retain that, I'm going to retain that.
Yeah.
I want to know what is the probability that I'm going to stay.
You can stay,
Mhm.
it's the probability that one of those is less than your view.
See, Robert said something.
I was thinking of like 1 minus, but.
1 minus, right? You're either going to do that or you're going to do that. But I don't want to do either, I just want to stay, right? So that'll be the complement of these two, correct? So probability of staying, I'll call it theta to theta, is 1 minus 0.5 minimum of probability of theta plus 1 over probability of theta called 1 minus 0.5 minimum of probability of theta plus 1 over probability of, oops. No, that looks the same. Theta divided by, I keep saying probability, my bad, it's the value, density, whatever.
Like, I know
It's a number.
proper to write the P, but you could just put like a little R just to remind yourself.
Yeah, I should, right?
Yeah.
But then,
I've been doing that, just to make it so that when I go back later, I'm not gonna get confused.
I don't know, maybe because, I just came from 2023. The book uses P of A instead of PR of A. So,
I would use the R.
That probably-
PR, yeah,
I learned P,
PR is the correct thing.
but
Formal.
it's just a letter.
Um,
And that's the word formal. Well, does formality really matter?
Well,
I mean-
if they're never gonna go on.
I know it's confusing. I thought of changing the notation, but then if you guys went back and read the book, it'll get more confusing, so which is why I'm sticking to it.
So the book just uses P for everything?
I think they're distinguishing lowercase b and uppercase b.
Okay.
But I am going to introduce something because I don't want to take the approach what the author did. Going from current state to the state higher than the current one, I'm going to call it as P plus. Going from current state higher to lower, I'm going to call it P minus. Going for, or staying, I'll just call it as P zero. You have this graph, right?
Yes.
Okay, we'll save this for our simulation next time. And let's see if we can hit that target distribution. We will. So the goal is to come up with the transition matrix. I'll show next time that for all cases, we will get closer to the target distribution, or we will get the target distribution. Good. Same up here, theta minus 2, theta minus 1, theta plus 1. Yes. Going from theta minus 2 to theta minus 2, what probability should it be?
P0.
P0. Yes. Going from theta minus 2 to theta minus 1.
Plus.
P plus. Theta minus 2 to theta
0.
0. How about that one? Theta minus 1 to theta minus 2.
Minus.
P minus. Theta minus 1 to theta minus 1. 0. theta minus 1 to theta, p plus 0,
You made some matrices like these.
theta, theta to theta minus 2, 0, theta to theta minus 1, minus, theta to theta, 0, theta to theta plus 1, plus, yes, theta plus 1 to theta minus 2, theta plus 1 to theta minus 1,
0,
theta plus 1 to theta,
p minus
theta plus 1 to theta plus 1,
0.
Explain that project we did.
Yeah.
Lines, I wrote up like a whole 6 case version of it. Took a whole whiteboard.
right? So, do we see a pattern here?
That's the heck. And then down,
It has a name. I went over this in linear algebra, Stephen. What type of diagram is it?
ooh, hold on, I heard this recently. Use these terms. It is. Offset.
Offset.
I don't remember what kind of diagram it's called.
Block that.
Which one?
Block.
Block.
So this is the part that keeps on going, you know, in both sides. This is the block that will keep repeating. And that is a proper transition matrix. Do we agree? Doesn't matter which row, which column you take, if you add them, it'll become 1. Yes? Add p plus, p0, p minus 1. P minus, p0, p plus 1. And every single value is a probability. Is it symmetric? Yes. Transition matrix, symmetric. Is it positive? Definite? Yes, it is. Does that make sense? Now, the goal next time before we do the simulation is to pick a steady state distribution, which would be the target distribution. And if I multiply the target distribution by this matrix, I'll end up getting the target distribution back. So that goes to the steady state concept that we talked about. Yes, once you attain the steady state, the next time you make a transition, you will still be in that steady state, correct? Yes, so if whatever distribution that you're multiplying the transition matrix by is the steady state distribution, the result of that matrix multiplication will be the steady state distribution, which is why we call it the steady state distribution or target distribution. Once you keep on going, eventually, when you take the steady state distribution, you will end up in the steady state distribution. So what we're trying to say is we will be going back and forth, back and forth, back and forth. But eventually, we will start getting closer and closer to that target distribution over several samples. But the moment we hit that target distribution, or we get closer and closer to it, we'll be very rapid in achieving that target distribution. Once that is attained, you will stay there. Think about the drunkard's walk. This way, you're going back and forth, back and forth, back and forth. But you get really, really close to your house. And what do?
Just keep going.
Speed up really fast so that you can just get in, right? That is your target. And as soon as you get to the target, you're just settling at the target. Does that make sense? So,
Because then you're only going back and forth inside your house.
true,
You'll lay down.